Here we're looking at some more basic concepts in probability. Now you might have seen this exclamation mark symbol before, and it's the first time we're going to really be able to use it in a useful context. So a lot of probability questions require you to work out how many different things can happen and then choose out of those things the ones you're interested in. So I'll give you an example of how this symbol here might be able to help us with that. So in the cupboard, I was looking for some mugs, and I've managed to find some. I've got this Parkside school mug. Very good. My friend's mug from, I think, the night before Christmas. This mug with a picture of another friend on it. That's a normal thing to have in the house. Cambridge Maths Hub mug, obviously, and no collection of mugs would be complete without Mr. Reed's Chrissy Cadillac mug. Now, if I was going to try and arrange these in as many different combinations and orders as possible, how many would I be able to do? Well, the answer is this. And many of you will know, let's adjust this down here, many of you will know that this is 5 factorial, and it means simply 5 times 4 times 3 times 2 times 1. And 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1 and so on. So the reason this is a useful calculation here is because if we look at the mugs again and think about it in terms of the number of choices I've got as I start to make my arrangement. So if I want to pick my first mug for my arrangement, I've got a choice of all 5. So I could pick any of them, and let's say I pick this one here. I could have picked any 5. And then for my second choice, well, I've already picked this one, so I haven't got 5 choices anymore. I've only got 4. So I maybe pick this one, and then I've only got 3 choices, and then just out of 2, and then the last one, no choice at all. And that's exactly what this calculation here is doing. I could have had any 5 initially, then any 4 remaining, then any 3, then any 2, any 1. So the number of total combinations is going to be the answer to this calculation. So in this case, we could work it out. 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. There is a button for this on the calculator as well, which you may have seen if you look very closely. If you can see that in the light, it's a bit more clear there. You can see the factorial button is right at the top here in the yellow. If we do 5, shift and that, we'll get our answer 120. Now you won't see the factorial symbol very much at GCSE, but the idea is going to be here a lot. So we continue looking at the cups. Let's put these back over here. Another very common type of problem you'd be asked is how many different ways can you choose things? How many different ways can you arrange things? So in the cupboard, I also had some tea, which I don't really drink, and some coffee, which I drink a lot of. So if I was trying to make a drink in the morning, I have 2 things I can combine here. I can have any of these 5 cups, and within that I can have either of these 2 drinks. So how many different choices do I have? Well, that calculation is going to be this one here. Any 5 cups, and for each of those 5 cups I could put 2 different drinks in there. So we're going to combine those choices and do 5 times 2, and obviously get 10. Now you can make this more explicit with something called a sample space diagram, which looks a bit like this. Now these are extremely useful in probability situations. Basically show you everything that can happen. So across the top I've got all the different mugs, got the Chrissy Cadillac, Parkside, Night Before Christmas, my friend Joe, the Maths Hub mug, and then down here the 2 different drinks, coffee and tea. And then within it I've listed every single combination of those things that can happen. So this one here is the coffee and the maths mug, this is the tea and the Parkside mug, and so on. So with this diagram, I can see clearly there is 10 different combinations like we saw from the previous calculation. We can also state probabilities. So if I wanted to know what the probability of drinking coffee out of the Parkside mug was, I'd look on here and I'd see that there is one of those combinations out of 10 possible combinations. And you do different things. You can say, what's the chance of picking either the Parkside mug or drinking tea? In which case you can see, well, there's 5 teas and then there's an extra Parkside mug, so that would be 6 out of 10. So the sample space diagram is really helpful for answering those kind of questions. Always a good idea to draw those if you're not sure of exactly what's happening. One final concept we need to be aware of is this: things that are mutually exclusive. So that's a phrase that just means that two things cannot happen at the same time. So in our example here, it's not possible for me to drink out of this mug and this mug. Well, let's just assume it's not possible. It's not a good idea. So I'm not going to be able to drink out of two at the same time. So those are mutually exclusive events. More obviously, it's something like rolling a dice. So you cannot roll a 2 and roll a 6 at the same time, so those two would be mutually exclusive events. When that's the case, you can do something very important. You can add their probabilities together. So if I want to know what's the chance of this or this happening, because they're mutually exclusive, I can just take the probability of this one and this one, and I can simply add them together to get my answer of 2/6. They can only do that if they can't happen simultaneously. Because if they can happen simultaneously and they're not mutually exclusive, there'll be some overlap and this calculation then doesn't work. So an example of that is, what's the probability of somebody choosing to study maths? What's the probability of someone choosing to study history? Well, if we just put some random numbers to that, let's say the chance of someone choosing to study maths is going to be, we'll do it 60%, and history, maybe it's 45%. Well, you can see already from those numbers that if I was to ask the question, what's the chance of someone choosing to study maths or history, it doesn't really make sense to add those two together, because then we're saying it's 105% chance, which doesn't make any sense. You can't have anything more than 100% probability. The reason that's happened is because somebody could choose to study them both. So they're not mutually exclusive. So you get a big overlap of these two probabilities. So you can only add them together if they are mutually exclusive. There is one more mistake here as well. Obviously, the chance of someone studying maths is actually 100%. Try the questions.